Colleagues, without wasting time, our last and final presenter for this session is Professor Bagula. He received a PhD degree in communication systems from the Royal Institute of Technology in Stockholm, Sweden, and MS degrees in computer engineering in University Catholique de Louvain. I hope I'm pronouncing that well.
Okay.
And yes, sir. And in Belgium, and computer science at the University of Stellenbosch in South Africa. He is currently a full professor and head of the Department of Computer Science at the University of Western Cape, where he also leads the Intelligent Systems and Advanced Telecommunication Laboratory. He is also an extraordinary professor at the ESIS Salama, where he's in charge of spearheading the institution research agenda. Professor Bagula is a well-published scientist in his research field. His current research interests include data engineering, big data technologies, cloud, fog, computing, network, softwareization, like NFV and SDN, the Internet of Things, including Internet of Things in motion, the tactile internet, data science, including artificial intelligence and machine learning, which with their applications in big data analytics and next generation networks, including 5G and 6G. Professor Bagula, it's an honor to let you present to us on building local communities of practice, COPs. Over to you, sir.
Okay, thank you very much. I've been given 20 minutes. I hope that I'll do it in 20 minutes as you suggested. So thank you very much for giving me the opportunity to speak in front of this audience. So the title of my presentation is Cyber-Physical Systems Security Using CPS IoT Surveillance. So please go ahead with the next slide. So, and the outline of my presentation will be as follows. I'll start with an introduction, just to put things into perspective, introduce the topic, why are we doing this, and explain what are the methods that we'll be using. This will be followed by the CPS IoT surveillance model and approach that I'm proposing. Finally, I'll present some performance evaluation of the model that we have implemented so far. And at the end, we'll summarize by concluding the talk with some suggestions also for future research work. So please go ahead. So in the introduction, I'll be talking about the cyber-physical systems. I'll present some key issues in the cyber-physical systems in terms of security. And later on, I might talk about the CPS Federation relevance, the integration of different models in order to solve.
Apologies to interject, Professor.
Yes.
My technical colleagues are asking that, is it possible for you to share your switch on your video for the online participants so that they can be able to see you?
Oh,
okay, switch it on.
So yes. It's switched on. Can you see me?
Yes, we can see you.
Yes, okay. So, so let's carry on. Next slide. So, as you see in this slide, I've presented what is a cyber-physical system, because we are talking about cyber-physical systems here. So we see that we have a system which has two parts. The physical space, a part which is controlling the physical space, it means that your environment, yourself, and all the objects of the real life that you are controlling. And another part on the right-hand side is a cyberspace, which is your cloud, which is your machine learning, everything that is a cyber in this context. And both spaces are connected by what? By a communication network. And this communication network could be kind of, let's say, a remote one. It could be also something which is not necessarily remote, but close. And in that case, we'll be talking about sub-physical systems or network control systems. But today we are talking about sub-physical systems. Next slide, please. So in terms of deployment, that's how we deploy these sub-physical systems. You can see that, we have our environment here. So the data is pushed from the environment, which is being controlled. It could be a human person who has his Fitbit. He's been controlled. His vital signs are being controlled. It could be in a hospital somewhere. It will be an e-health kiosk in a rural area of South Africa or Africa. Anywhere, it could be the pharmacy, whatever we are controlling. This data is collected by sensors. The sensor push this data into fog infrastructures, which are much more closer to the users. And from the fog, it will be pushed into the central cloud, which is in the center of the network here. So another illustration is showing, how this is being deployed. You can see that we have different layers here. It started with the data collection. It started with the devices, which are IoT devices, which are launched into the environment that we are controlling. This goes to the fog infrastructures, which are kind of small cloud infrastructure, which can do the same job as the cloud infrastructure. They have storage, they have servers, they might have machine learning algorithm, but they are smaller and they are closer to the users. And from the fog, it could be sent to the cloud infrastructure. But now, the problem that we have with all this is what? Is that, the next slide, please. We can see that this is the architecture of proposed by ITU and another RERC architecture for the part that we call the CPS IoT. So we have different layers, the device layer, and you can see in this deployment, this is mimicking, in fact, the deployment. We have the device layer, we have the network layer, we have the service and application support layer, and the application layer, where all the services are provided to the users. But what has been found is that the CPS IoT, remember the two parts of the CPS, sub-physical systems, the CPS, the subspace, which is controlled by the CPS IoT, and the second part is the subspace, which is controlled by the CPS cloud. And both spaces are communicating through a network. So, but it was found that, the CPS IoT was the most, let's say, attacked part of the CPS, and which can have a lot of impact on the CPS. When they are attacked, they can have they can bring a lot of damages, damages which can even include human life losses. So, and that's why we are interested in this, the security of the CPS IoT. Secondly, also, we have realized that in the CPS IoT, some of the attacks which are the most prevalent, the most used, are first of all topology attacks, and secondly, traffic attacks. There might be many attacks. Please pass the next slide, as shown in not this one. Go ahead. Go ahead. So you could see there is a taxonomy of some of the attacks here. They can be categorized into traffic, topology, and resources. So, but what we are interested in here is the traffic and the topology attacks, because these are the attacks that we found that have been very common in the field of CPS IoT. Next slide, please. So this is illustrating, let's say, a CPS attack. So for those who know IoT very well, we have what we call, when we have a deployment in mesh, we have protocol like RTP and also LibP, which are based on what we call collection tree model. So it means that you have your graph of the network, your network. So an algorithm which is implemented there, the protocol which is used is using a collection tree approach in order to build a tree which is rooted at the gateway. in order to collect all the information from the nodes of the IoT system. So that's what we call collection tree protocols. And one of the most popular, and the one which has been standardized, is the RPL protocol. So here we have an example where we have our graph, the graph of the network that we are trying to control. It could be some, let's say, some nodes in hospitals in Gauteng or in Cape Town, isn't it? And we have some nodes which are there, IoT node, and they are communicating. We are collecting the information from the root which is the one, node one. And the collection tree, which could be built from there, is this one here we see, the rooted at one. All the nodes are collecting the information and pushing the information to the node one. But there could be some ways of attacking this network by creating a circle, as you see in red here. The information, let's say, instead of going from 5 to 2 to 1, what will happen? The information will go from 5, it will go to 8, 7, 3, 1. So you create some kind of circle into this topology. This is an example of a topology attack in the network. So also it can happen that what will happen? There is always also traffic attacks which could be done on the network because some of the other protocol, one of the most prominent protocol which is used in IoT is the MQTT protocol. So this protocol is based on the TCP for transport of the information. And any attack on the TCP, as this protocol is using TCP, attack on TCP like hash ping or bien LOIC or LOIC attacks can have an impact on your IoT network. And these are the two types of traffic that the attacks that we are interested in order to protect our IoT network. So please carry on. So carry on. So now let's consider what we are proposing as a solution to this. So first of all, we'll start by presenting a CPS security architecture. And this will be followed by topology surveillance model. And after that, the traffic surveillance model. And in section 3, we'll present the result of these models. So go ahead, please. So this is what we are proposing as a security architecture. So what you see here in the security architecture is based on what we call the Lambda, big data architecture. Why are we talking about combining big data and security? You'll understand that, IoT devices are producing a lot of information. And on a sampling rate which could be very high, and which will happen, we'll go into the realm of big data management. So you need, first of all, when you do anything in terms of security, looking at how the big data, what will be the big data architecture that could be using. So here what we did, we adapted the Lambda architecture, big data architecture, to do our work where we can combine real-time detection and also batch detection of whatever is happening as attacks. So here in the architecture, what we have a unified log, which is receiving the incoming connections, IoT connections. So these two connections, any connection will come, it will follow the two paths. We have two paths. The hot path, which is the real-time path, in fact, in the speed layer, and we have the cold path, which is everything which is batch processing. And when we are talking about batch processing, obviously, we understand that we are using machine learning here, historical data. So what will happen, any incoming call which is coming, it will be directed to both layers. In the speed layer, what will happen, it will be, we'll have a real-time analysis of the attack, the connection. So through real-time analysis using network parameters, we'll be able to classify, we'll arrive to a real-time classification of any connection. So a connection which is arriving, we might know that, okay, this is a normal traffic. It could be, let's say, a attack traffic like hash ping or LOIC or any other attack. And when we have classified, we'll take this result, we'll push it to the saving layer of the cold path, so that it could be used, for doing what? We know that we are building a certain historical data here, a data set which is unlabeled yet. So we can label it using the speed layer. Because as it has been already classified, we can say, okay, now the data which has been collected here could be classified, labeled as normal connection attacks of type hash ping or attack of type loic. Okay, and from there we'll be able to deploy machine learning to provide some result to our analytics client. So,
Professor, 3 minutes.
Okay. The cold path is the same. You have unlabeled data, labeled data because of from the speed layer and so on. So, okay, let's carry on now. Go on. Okay, go on. Go on. Okay, go on. I've explained this. Please carry on. So the topology surveillance model, what is about? It's just a way of saying, okay, we are replicating any topology that we are, if we have a mesh network in IoT. So we are doing what? We are mapping the physical network topology to what we are doing at the gateway. So this is in-memory model and the lab network topology. Okay, the same. So that when it's arrived, the information arrived, we are building the topology so that we can compare both topology and know if there has been anything which has been tampered with the topology. Carry on, please. Please, carry on. Okay, this is the algorithm. It's just a breadth first search algorithm which has been implemented by the gateway in order to build, replicate the topology, the physical topology at the gateway, in order to compare with what is happening with the real top, if there is an attack. Let's carry on, please. Go on. So this is just an illustration of how this could be used for detecting sinkhole attacks. Okay, go on. Okay, so in terms of traffic surveillance, go on. So the objective here is to protect the MQTT protocol, which is the de facto standard protocol for IoT data transport. Okay, so by doing what? By detecting typical attack on TCP, and specifically those that we use, we created the real attack on a real network using the hash ping and loic tools. So in order to protect MQTT, okay, and the strategy that we did is generating a data set of attacks, hash ping and loic attacks, label the data set, following what we use as architected there, and use the generated data set for machine learning classification and prediction in the serving layer. So let's carry on, please. Okay, this is the algorithm for CPS IoT surveillance, the real-time part of it, using network parameters. Go down. So the machine learning that we use, KNN, logistic regression, ANN, stacking, and other. So random forest and other. So carry on, please. We'll go to the results. So now, let's look at the results. The results have been presented in terms of topology surveillance. So the parameter that we use for topology surveillance, we did the test in the Kuja, using the Kuja platform, which is a platform Contiki with an operating system, which is a platform used for emulating IoT network. Okay, let's carry on the result that we got. Carry on, please. Pass the slide. Okay, so in terms of result that we get, the topology replication process, we have here the success rate. We can see, according to the topology of the size of the network, we can see that we have 100% success rate of detecting the attacks. But when we arrive at 110 nodes, we started seeing that the success rate is started dropping. So our algorithm started losing its precision. So now we look at also, it's very important in terms of IoT, looking at the energy consumption of anything that you bring new in terms of IoT. So we can see the average power consumption So obviously, we increase in terms of power, on terms of topology replication and non-topology replication. We see that we are increasing the energy consumption a little bit, but not too much. In terms of gateway power consumption also, so an order of 200 milliwatts is not too much compared to the gain that we get in detecting the attacks. And also in terms of energy usage of sinkhole. In that case, we are consuming much less because when you have sinkhole attack in the IoT network, you'll have this T-air and the retransmission, which will bring you to much more energy consumption here. Almost the double of what we are using when we are using the TRP. So which show that our TRP is a very good thing. So let's carry on, please.
1 minute to round off.
We present, well, yes, you said?
1 minute to round off.
Yes, 1 minute, is almost there. I'm almost there. So this is the false positive and false negative. Also, we are much more interested by the false negative because that could be quite dangerous in terms of security attacks. And you can see that we are still doing good in terms of topology up to a topology of SAS 110. So let's carry on, please. Let's look at the results very quick of traffic surveillance. Let's go on. So in terms of traffic surveillance, so for our real-time traffic performance, you can see that we are getting up to 96.5% of performance, which is very good, the algorithm that we implemented. Let's carry on. So this is the result of looking at everything which is a confusion matrix. So let's carry on, please. It was not also bad. Let's carry on. Let's go to the machine learning part. So the machine learning part, this is, the parameter that we use. Carry on. So the algorithm that we use. So the results are these that we found. So we deployed, different machine algorithms, KNN, logistic regression, INN, random forest, and we found stacking. And what we realized is that our random forest was performing the best in terms of not only performance, accuracy, and other, but also in terms of also recognizing confusion matrix. Let's carry on. I'm almost done. So this is a confusion matrix, and you can see also what is happening with our random forest. It has less, it's more accurate, let's say. So let's carry on. The last one. So, and this is what we are finding. In terms of accuracy, sensitivity, error rate, specificity, this is what we have. And the error rates also, you can see again, as I said, random forest is performing quite well in terms of the model that we have implemented for traffic surveillance. Carry on in the last, that's what we did. And that is the end of what we are presented. Carry on. The last slide is just what I presented, a new CPS security architecture, a topology surveillance model, and a traffic surveillance model with the results. Thank you very much.
Thank you, Professor Bagula, for for that insight. We really appreciate sharing with us cyber physical systems, cyber attacks. We really appreciate the information you've shared with us. Colleagues, I can just allocate a minute just for a question or so for our speakers. I've got a hand. Professor, I see you. I see you.
Just a quick question. The role of the fog nodes seem to be a little bit vague. Also, when you're dealing with older, very simple sensors, they don't use TCP, which seems to be the basis of your security model. And of course, the sensor to the fog node could be a major open door in terms of security. How is that handled? Thanks.
Okay, thank you very much for this question. As I mentioned, these are protocols. MQTT is one of the protocol which was invented by IBM, and is becoming the de facto standard in terms of IoT security. And these protocol is at the layer 5, but it uses a transport protocol TCP. So instead of attacking MQTT directly, you can attack TCP, which is a transport protocol used by MQTT, and at that moment you can access your sensor node and attack your IoT network. Am I?
Thank you, Professor. I think the second question from Kasim.
This is very quick to Richard. You said bio-inspired algorithms can jump from local minimal to look for global minimal. How do they do that? Because most typically you expect the algorithms to converge depending on the starting point.
One of the main points of many of the swarm bio-inspired algorithms is randomization. So, it might find a global minima, but, depending on some random value, it might stay in that, or it might jump out and keep searching for a better global minima.
So that would be existing section.
Yes, this is one of the problems with bio-inspired algorithms. They do take a large amount of time, and it's also a venue in terms of performance computing, etc. Thank you.
Thank you so much to all our presenters that were physical and those that were presenting online. Maybe note the presenters that are online will make some arrangements for you to get your token of appreciation from us. We will see how to get that. Maybe just a round of applause to all our presenters for this session.